Hello, this is a presentation on solar sailing. It's by Benjamin Applegate, Kenan Thumar, Jay Valdovinos, Jackie Hugh, and Bryce Leonard.
In the 1860s, James Clerk Maxwell published a paper on electromagnetic fields and radiation, which theorized light had momentum and could exert a pressure. In 1925, Friedrich Xander published a technical paper that included an analysis of solar sailing, writing that one could apply small forces using light pressure. The concept was popularized in the 1970s by Carl Sagan and various mediums, describing the ideal of sailing on light using a structure that could reflect photons. The first true design effort to create a solar sail began in 1976 at the Jet Propulsion Lab as a proposal for a mission to rendezvous with Halley's Comet. There are predominantly two types of solar sails, reflective and diffractive. For reflective solar sails, the surface of the sails are made of a highly reflective material that uses the force of the impacting photons to propel the spacecraft. One drawback of these solar sails is that the sail must be pointed along the same axis of the incident sunlight to create a sufficient force. The concept of diffractive solar sails was first proposed in 2017 by researchers at the Rochester Institute of Technology. Advances in material design and fabrication techniques allowed for the creation of smaller gratings in thin metamaterial films that make up the structure of the solar sail. These gratings cause the light to sprout out in all directions when the incident photons impact the solar sail, making more efficient use of the sunlight. Diffractive solar sails are theorized to be less susceptible to heating from the sun and can create a propulsive force even if they're not directly oriented towards the sun, unlike reflective solar sails.
Solar sails can be used for interplanetary missions, allowing spacecraft to travel between planets within our solar system without the need for traditional propulsion methods like chemical rockets. This could significantly reduce times and mission costs compared to conventional spacecraft. Solar sails can also be used for station-keeping maneuvers in space, allowing satellites and space stations to maintain their position relative to other objects without expending traditional propellants. This could prolong the operational lifespan of satellites and facilitate complex orbital configuration. Solar sails could be employed for space debris mitigation efforts by gently nudging defunct satellites and debris into lower orbits where they would eventually burn up in Earth's atmosphere. This could help reduce the risk of collisions with operational spacecraft and satellites. Solar sails could be equipped with solar panels to harness sunlight for power generation, providing an efficient and renewable source for spacecraft systems. This could extend mission duration and reduce the reliance on traditional battery or fuel-based power systems.
Attitude, dynamics, and kinematics. Propulsion. Solar sailing involves the use of solar radiation pressure on large reflective sails to propel the spacecraft, and through the usage of the solar sails, despite solar radiation pressure being low, a spacecraft can continuously be accelerated across and can be more effective than traditional propulsion systems when navigating across space and transferring between planets. You're also able to transfer orbits much easier and simpler than using traditional propulsion. The normal methods are not suitable for attitude controls of solar sails due to the moment of inertia and perturbation torques being way larger than those of the traditional spacecraft, and due to the changing solar sail dynamics. There are three types of attitude control methods for solar sails. Spin stability control, in which the solar sails deploy and maintain flatness using a centrifugal force, reducing the structural mass. However, executing large attitude maneuvers is challenging due to the substantial angular momentum from the sail's spin. Next, there is passive attitude stability, in which the specifically designed sails maintain the desired orientation without being given active control inputs. They can be designed with optimization based on the orientation in mind to maximize thrust and trajectory by aligning with the incident sunlight. There is also three-axis attitude control, in which is a mixed control system using the three axes, the yaw, pitch, and roll. Using both passive and active attitude controls, you are able to move the center of mass and change the center of pressure to get desirable control effects. Center of mass can be adjusted from gimbal masses method or through using sliding masses, and the center of pressure can be changed using the control vane method or the shifted and tilted wings method. This is an example of the closed loop system for controlling the sail attitude. The system includes the nonlinear system, LQR gain matrix, and the desired reference input sail position, as well as the radius from the sun. The radius from the sun is included as an input for modeling the interaction with orbital dynamics, and it allows the nonlinear rotational dynamics to continually change as the radius from the sun changes. The reference input allows the desired sail orientation angle to be specified for the controller to move the sail to that position, and the equilibrium position of the sail is any point where the sail and control boom angular positions are equal. Thus, the reference sail position is applied to both the sail position x1 of t and the control boom position x2 of t.
Solar cells have several key technologies that hold significant value for their functionality. The noticeable ones are its design concept and material selection. Solar cells rely on the principle of solar radiation pressure produced by the sun to propel the spacecraft. By adapting this concept, solar cells can provide spacecraft with a continuous acceleration that could eventually surpass the speed provided by a rocket engine. And this math is done through calculating the force produced by the solar power over time at the distance of 1 astronomical unit. And additionally, solar cells are designed to be extremely lightweight in comparison with traditional propulsion systems. This concept is beneficial for propelling deep space exploration vehicles. And lastly, with the concept of harnessing photons or particles of light in exchange for momentum, solar cells can also utilize such energy through lasers when it is far away from the sun. On the other hand, material selections is another key technology that gives solar cells an advantage when it comes to propulsion selection for spacecraft. Materials such as CP1, which is an aluminized and temperature-resistant material made for the NASA solar cells, or aluminum reinforced mylar and Kapton for the Planetary Society solar cells, are all extremely lightweight materials that are made to approximately 1/4 the thickness of a trash bag. And this provides less mass for propulsion system, which allows additional payload mass tolerance. And furthermore, reflective coatings are essential, and another essential technologies developed for solar cells. With a metallic reflective coating such as polyimide, mylar, and polished aluminum, it increases the efficiency in harnessing sunlight for propulsion while minimize solar energy intake to prevent overheating.
Solar sails have the potential for efficient interplanetary travel, but for now most are used for power generation, station keeping, and orbital maneuvers. Propulsive forces are generated by photons impacting the film. Continuous solar activity allows for continuous acceleration, and there is potential that the spacecraft can be propelled to higher velocities than conventional means. Traditional attitude control methods are not viable due to complications with the structure, so 3 types of unconventional control methods are used: spin stability, passive attitude stability, and 3-axis attitude control.
Questions?